Hello, everyone, and welcome back to Historical Geology 1404. Today is Lecture 3, but before we jump into that, as always, the floor is yours to ask any questions you may have. What do we got?
What exactly did y'all go over on Tuesday?
What did we go over last time we met? Rocks and minerals. Rock cycle, different types of rocks, all of that. Quick recap. Today is going to be a quick recap of plate tectonics and mountains. Okay. Lab 1 was also assigned last time we met. It's very straightforward. I did post the recording for that lecture, so you can go back and watch that if you have not yet already. Yeah, good question. Thank you. What else? Jocelyn, what's the occasion with the flowers? Your boyfriend gave them to you. That's a classy move. What was that?
He's like, oh, I went to Starbucks. And I just wanted to get you something. He just goes into my classroom and gives it to me. My teacher's like, next time you do, at least get this.
At least get. Nice. Well, it sounds like he takes care of you. So, gentlemen, you listening? Okay. Yeah, Angel says no. All right.
I mean the flowers.
Yeah, you need the flowers? Well, I'm not going to give them to you.
Orchids, please. Orchids. By the end of the
Orchids?
day.
All right. I'll hold that little tidbit of information. Angel likes orchids, but I'm still not going to get you any. All right. I'll remember it, though. Thanks for telling me. Okay. Any other questions? Last chance before we get started? I mean, obviously, it's not the last chance. You can literally ask questions anytime, but you know what I mean. No? All right. Plate tectonics. The whole reason behind plate tectonics has to do with the composition of the Earth and the way that heat moves through that composition. Recall that Earth is separated into a series of layers. We have our core. At the very center, a solid iron-nickel alloy core. It is extraordinarily hot. It would be melted, except it's under too much pressure. The next layer out from that is the outer core, still an iron-nickel alloy, but it is in a liquid state. This is the only layer of Earth that is in a liquid state. Why is it in a liquid state? Because it's not under as much pressure as the inner core, and it is hot enough to be melted, and thus it is in a melted state. Outside of that, we have the mantle, the thickest layer of our planet. Okay? That is in a solid state, though I would call it squishy, right? In the same way that Play-Doh is a solid, but can be moved, can be formed. It's flexible, it's malleable, okay? As pressures and temperatures fluctuate in the mantle, that material moves just like Play-Doh does under pressure. And then finally, we've got the crust. The crust being the part that we live on, so we kind of like it a lot, don't we? The crust is the thinnest. Compared to the others, it's paper thin, right? It's pretty thick to you and me. 15 kilometers is a lot to go through, but not when you're considering 6,000 kilometers to the center, or through our planet, right? So, the oldest rock that we have on the crust is about 4.4 billion years old. That was found in Australia, right? How does crust like that survive that long? Well, not much of it has, which is why there are only a few places around the world that we can find crust that old. We had no idea that the Earth was that old until we found that crust. And then we were able to figure out that the Earth is even older by taking samples off the moon and testing those, right? Okay, that's where we get that 4.543 that pushed the date of the Earth back another 140 million years or so, right? So the crust, mostly made out of these 8 elements, okay? Most of which silica and oxygen, silicon and oxygen. Why would silicon and oxygen be so common on the crust? What do we know silicon and oxygen make?
Silicon tetrahedron.
Silica tetrahedrons, which form the basis for all silicate minerals, right? Silicate minerals being those that form from the crystallization of lava and magma, right? And thus, because our crust is largely made through those processes, we have a lot of silica and oxygen on the crust, okay? Now, the crust is a lot thinner at the ocean than it is on the continents by a significant margin. About 5 kilometers on average thickness in the ocean, about 35 on land, okay, for continental crust. That's very thick. We have never drilled through the crust all the way. There is an effort underway to do just that, though. I believe the deepest drill bore that has ever been done was 15 or 17 kilometers deep. It was in Russia. There is a group that is working on building a drill that does not use a metal drill head, because it would melt at the temperatures further down, right? They want to drill, I think what they say, they want to go 30 and then 40 and then 50 and 60, see how far they can push it. But instead of using a metal drill, they are going to be using high intensity lasers. Yeah, seems pretty cool to me. So, the mantle takes up about 82% of the total volume of our planet. This includes the upper and lower mantle. The upper mantle being mostly rigid, stiff rock, very hot, but still in a stiff, rigid state, a true solid. The lower mantle being squishy, flowy, but still a solid, just like that Plato example I gave you. This all has to come down to the relationship between heat and pressure and the materials that are under those forces, right? Physics, y'all have taken physics at some point? Okay, so you know that if I were to pressurize water, it would take more temperature to boil it. Did you ever learn that? If I have higher pressure on water, it will not boil as easily. On the other hand, if I have lower pressure around water, it will boil easier. Which is why, I mean, you may not ever have heard this, but fun fact, if you were all of a sudden in space, just exposed to that hard vacuum, you would simultaneously boil and freeze at the same time. Why would you boil? Because there's no pressure, and the radiation from the sun causes the water in your body to turn into steam. Why would you freeze? Because it's so cold. Regardless of the temperature out there, the lack of any pressure whatsoever would allow the water in your body to be instantly fresh vaporized by even the smallest amount of radiation, okay? Sorry, that's a very grim example that I gave, but you get the point, right? Higher pressure for water means higher temperature to boil it. Now let's take that concept and apply it to rocks or other different materials. Under higher or lower pressures, melting points will be different. Okay? So while the mantle is hot enough to, under normal circumstances, be melted, it is too pressurized to actually be melted. Okay? And then we've got the core. There is a fantastically horrible movie called The Core, which I believe is one of our options for our silly geology movie night this semester. Okay. I'll be sending out that Google form here in the next week or two so we can figure out what day we want to have our silly movie night. For those of you taking the class online, you are more than welcome to join us in person or watch the movie on your own. I cannot record it or broadcast it for you, though. So you will either need to come to campus to watch it with us or watch it on your own, rent it if it's already on a streaming service, whatever the case may be. And I will be sending out a survey here soon asking which movie we should watch. For those of you that came to last semester's, it was fun. It was a good time. Okay. The core is separated into two sections. The outer core, pictured here, right, which is liquid iron for the most part, and other dense elements like nickel and uranium and a bunch of other radioactive elements down there, okay? It's that radioactivity that is generating most of the heat that keeps it in a melted state. It's very important that this outer core remain in a melted state. Why? Well, because iron is magnetic, right? You're familiar with this. Iron has magnetic properties. The inner core is also iron and therefore also magnetic. And so while you have an outer liquid core of iron and an inner solid core of iron, the interaction between these two iron bodies generates what we call an electromagnetic field. Our inner core, we believe, is rotating at a different speed and even different angle than the rest of our planet. While our planet is spinning in this way, our core could be spinning about the same direction, just slower, or it could be spinning a totally different direction. Or it could be doing this, right? Try doing this, by the way. It's like trying to rub your belly and pat your head at the same time, right? Now, why is it spinning in a different direction? We think it has something to do with that impact that made our moon in the past, okay? The two planets that collided with each other and their combined mass has made the Earth today. Whatever planet was in this orbit previously was maybe not even spinning at all. Maybe it was spinning a totally different way than Earth is now. But the collision of that planet with ours set it on its current spin through space. And because the solid inner core was buffered by a liquid outer core, it did not pick up the same momentum. So the outer part of our planet is spinning one way, and the inner part, the inner core, could potentially be spinning in a completely different direction. It's interesting, isn't it? It's like if I had a bucket of water right here, and I put a ball in that bucket of water, and that ball is just floating there, right? And then I turn the bucket. Does the ball spin? No. At least not unless I like really spun that bucket. Eventually, the movement of the water may start the ball spinning, but it would take a lot of energy to do that, okay? Thus it is with our inner core. Now, the interaction making this electromagnetic field is extremely important to our planet. Come on, camera, stay with me here. Why is it so important to our planet? Any ideas?
The what?
The what, exactly? No.
Like the magnetic field? Like
Yeah, why is the magnetic field so important to our planet?
like the cell phone in it?
Okay, so you're pointing out technology that we have developed that utilizes that magnetic field, things like GPS and cell phones, yeah? It protects us against radiation. Radiation from what? What possible source of radiation could be in our neighborhood that could be harmful to us? The sun. Yeah. What could it be? Not only the sun, but also cosmic radiation. Things like gamma rays and the such that are coming from supernovae that occurred hundreds of millions of years ago and are just now flying through our solar system. Things that typically would cause great damage to our planet and to us are deflected or dispersed through our electromagnetic field. Have you ever seen pictures of the northern lights? What you're looking at is our magnetic field deflecting or absorbing energy from energized particles coming through our atmosphere. Okay, that's what's happening there. They're ionized particles interacting with our magnetic field that we can see in our atmosphere. High in the atmosphere, right? So, this is very good for us. The continuation of our magnetic field is acting essentially like a shield protecting us from all this harmful stuff. What would happen if our magnetic field were gone? Radiation, a lot of radiation. What do you think that radiation would do to us and every other living thing? Deep fry us, exactly. Okay, we would not last long if our magnetic field were just gone. As a matter of fact, there is strong evidence to suggest that this is exactly what happened to Mars. Yeah, here's a fun little tidbit if I have not shared this with you yet. Mars, for sure, had running water. We see the old rivers. There's not water in them anymore, but the old riverbeds are still there. Deltas, okay, lakes we can see. We see where there was lots of glacial activity at the poles. We see evidence that Mars had an atmosphere, potentially not too dissimilar to Earth at one point. Potentially. We're still working on figuring that part out. So where did it all go? What happened to it? Mars is smaller than Earth, about 30%, okay? This means that it cooled off on the inside faster than Earth is cooling off. So about 2 billion years ago, we think, its inner core finally stopped whatever motion it had because the outer core solidified. Without that interaction between the liquid and solid core, there was no magnetic field produced. With no magnetic field being produced, that electromagnetic field could not deflect solar and cosmic radiation. The atmosphere got blown away by the solar winds, we call them. All that radiation moving through space constantly, we call it the solar winds. Water was evaporated off into space, and then Mars was left a barren, potentially now lifeless dust ball. Did life ever exist on Mars? Well, that's a question that people are trying to answer right now. The Perseverance rover landed there a few years back. If you've kept up with it, it's pretty cool. It's been traveling along a river delta, taking geological samples as it goes. I believe it's intended that 36 geologic samples from Mars are going to return to Earth by about 2035. I believe that's the plan. They're going to get picked up by spacecraft that they're going to launch here in the next year or two. That spacecraft is going to pick up the samples, swing around Mars, and come right back here. And then we will have Mars rocks here to test and see if there's anything like fossils in the rock or any evidence of life whatsoever. It's going to be a big moment. We'll find out. Okay. All right, tangent over. Let's talk about continents for a minute. Continents are less dense than the ocean crust around them. Even though the ocean crust is thinner, it is denser than the thicker continental crust. It's like if I had 6 inches of water in a tub, and then I got a 4-foot by 4-foot block of styrofoam, and I put it in those 6 inches of water, the styrofoam would sink to the bottom, right? No. Good. What would it do? It'd float right there on top of that water. What if I had 3 inches of water, or 2 inches of water, or 1 inch of water? It would still float on that water. Why? Because styrofoam is still less dense than water. No matter how much water I have in that tub, that styrofoam is still going to float on it because it's less dense. Okay? Same way that a continental crust that is 35 kilometers thick is going to be more buoyant on the mantle than the 5-kilometer thick ocean crust, which is more dense. Thus, our continental crust remains above the ocean level, while the oceanic crust remains the low point around which, or on top of which I should say, the ocean waters congregate. Okay? Now, plate tectonics. We learned that the mantle, the rock in the mantle can move, it can fluctuate, it can get pushed, it can get pulled, it can be manipulated. What's manipulating it? Transfers of heat. Okay? Our planet's surface is broken up into what are called lithospheric plates. Okay? Rocky plates. These plates are constantly moving, interacting with each other, crashing into each other, pulling apart from each other, scraping past each other. Convergent, divergent, and transform plate boundaries. Remember that? What is driving all of this? A mechanism called convection. Convection, simply put, is the rise of hot material and the fall of cool material. Anyone remember why hot things tend to rise above cool things?
Because they're less dense.
Why is it less dense?
I'll just expand. That way, they're like less dense.
Say that again, I'm sorry.
Heat makes things expand.
Heat makes things expand. Remember, density is a measure of mass and volume. I'm not changing the amount of mass in a given quantity of my rock. I am, however, changing the volume. Increase volume, maintain constant mass, density drops. Therefore, as this happens to the rock, and it becomes less dense than the rock around it, it's going to naturally rise above that rock around it as it becomes more buoyant. It rises close to the surface. But what's at the surface? As this mantle material is rising, it's going to encounter something.
The plates.
And the plates are make the
Crust?
crust. Right. Okay. So it encounters the crust. And that crust being made out of all these broken plates, something's going to start happening now. As our rising hot mantle material approaches the surface, it's going to start losing that energy. It's going to cool off. As it does and it starts becoming more dense again, it's getting shoved off to the side by newer, hotter, more buoyant material rising beneath it. It's going to get shoved that way or that way. Whichever direction it's getting shoved, it's going to create drag on the surface of the crust above it. Okay? So if it's getting pushed this way, it's getting shoved that way, it's going to create a force of friction on the bottom of the plate above it and pull that plate that direction. Now this is a cycle. It's a convection cycle. Hot material rises, starts to cool off, gets shoved to the side, falls down, heats up, gets and rises again. That is a convection cell, we call it. When you have two convection cells next to each other that are moving in opposite directions, so this part of the plate's getting shoved that way and this part of the plate's getting shoved that way, you have a divergent plate boundary. When you have two convection cells that are moving in the same direction, like so, one plate is going to run into the other, and they're either going to make a gigantic mountain range, or one's going to subduct under the other. Whichever one's denser will subduct, right? And then when you have two convection cells that are doing this, yeah, try doing this one now, right? Two convection cells that are doing this, moving in opposite directions next to each other. Yeah, it's hard, Aaron, isn't it? Yeah, they're doing this. It's going to cause the two plates above them to scrape past each other, like so. I love that you're all trying this now. Angel looked like he was winding string around his finger.
Yeah.
He's playing with a yo-yo over there. Okay. Any questions about convection? There is substantial evidence to prove that this, in fact, is the case. That plate tectonics is indeed how our crustal plates move. Prior to the theory of plate tectonics was something called continental drift, something that unfortunately is still taught in a lot of schools, even though the theory of plate tectonics was pretty well ratified by the scientific community in 1964, okay, or 1968, I should say, okay. Continental drift basically says the mantle is melted and our continents are essentially giant islands that are floating around playing bumper cars on an ocean of magma. Okay? That's pretty much what continental drift is. And that's what people believed for quite a while. And yes?
So what specific, like, I don't know, paper or like a movement said, hey, plate tectonic is what's actually happening?
There are actually, I couldn't point you in the direction of a single paper. There were plenty of people who helped develop this theory. Yeah, of course. Alfred Wegener, Marie Thorpe is someone who doesn't get enough credit here. Oftentimes, plate tectonic theory and associated not discoveries, I should say, but theories are associated with the work of Alfred Wegener, okay, which started well before this date of 1968. 1968 is simply when it was kind of generally accepted, okay? This work began well before that. Marie Thorpe was a woman, and back in the 1800s, right, in early 1900s, women in the scientific community were not considered the equals of men, as they were not in many other, parts of life as well. But Marie Thorpe is someone who definitely deserves credit for putting a lot of legwork into gathering data that eventually led to our current understanding of plate tectonics. So I want to put her name out there too, anytime I can get. Now, so the work of those two people would be worth looking into if you're interested in learning more. Okay, we owe them a lot for this. It is quite obvious when looking at their continents that at one point they were connected to each other, right? There are some continents that you just cannot dispute how obvious it is. South America and Africa fit together like gloves, like a glove on your hand, right? In addition to the fact that there are layers of rock on both continents that directly correlate with each other, you can go to the west coast of Africa and you can do a stratigraphic study of layers of rock on the coastline here, and then you can take a hop, skip, and a jump, quick plane ride over the South Atlantic Ocean to East South America and do a stratigraphic study of the rock layers there, and they match exactly. The only way that could happen is if this was one continent and that sediment was laid down across this entire area simultaneously. And then at some point, they broke apart, okay? How do they break apart? You get rift valleys. Rift valleys like what is happening in East Africa right now and what's happening along the Rio Grande River here in our neighborhood as well, okay? Where you've got all of a sudden some new convection cells start going and they're moving opposite directions. And it just so happens that the crust above them has a continent on it. Convection cells don't care, right? They're not going to say, oh, well, there's a continent up there. Let's move over here to the ocean. They're not going to do that. And so they're going to keep moving. And as they keep moving, creating that frictional force on the bottom of the plate beneath the continent's going to start stretching and thinning. As it starts stretching and thinning, it's going to start cracking, making faults. And through those faults come lava or magma, okay? And because the crust is stretching and thinning, that magma does not get as much opportunity to become felsic through Bowen's reaction series. And so more and more mafic lava is deposited on the surface, creating new ocean plate in the crack that now exists where that continent used to be. And that's how these two continents split apart. This was a mid-continent rift valley ridge, okay? Right there. And eventually the Atlantic Ocean came from the splitting apart of that continent. Yes?
So let's say like a convention cell was like right in the middle of a plate.
Yep.
Right?
Yep.
And another one is like right at the edge of a plate.
Yeah.
Another. So the one near the edge has more effects than the one in the middle. Maybe they have the same effects.
Yeah, it's not necessarily. First of all, I'm not entirely certain what you mean by effect. Like, which one is more powerful?
Well, which one like moves the plate more?
Well, plates are often moving at multiple directions. So I can have one convection cell causing my plate to move this way, and another one down here is causing it to also move that way. And so my plate could do this, or depending on which convection cell is more active, which one experiences the most movement, I can see something like this as time goes on, right? So there's lots of variation here. Convection is the mechanism. The movement of these plates is actually quite complicated. And this is actually a good thing to bring up because I have a short model video to show you, and it's quite fun. Now, I don't remember if it has music. I mean, I know it has music. I don't remember if I have this muted, okay? If it's not muted and there is music, please don't fall asleep. I don't know why they put the most zen music on this. It goes well with the video, but every time I'm watching this, I start nodding off, okay? So fight the urge. It's a really interesting video. The last thing I want to say before I play this video is to be defined as a supercontinent, this mass has to contain at least 75%, okay, of all the land mass present on Earth at that given time. Now, what you're going to see in this video is we start off with very little land mass. Okay, why is land mass forming at all? Convection cells causing these plates to interact with each other. Plates that originally started off as only oceanic plate. We started off with an ocean, just an ocean. There wasn't really anything poking above the ocean, but as more of these ocean plates interacted with each other, Bowen's reaction series took effect. More and more intermediate and then felsic material built up on itself and started making the land masses that were above the ocean because they were more buoyant on the mantle, right? And you'll see these land masses grow and grow and grow and grow as this effect compounds, okay? The other thing that I want you all to pay attention to is you're going to notice that initially the movements of these continents are jerky, okay? They're here, and now 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 they're here. And then you're going to notice a couple billion years in, things start getting a little more fluid, right? Why do you suppose that might be?
What do you mean fluid? Like they move better, or like more?
Let me play the video first, and then I will ask you this question. How about that? Instead of saying, you're going to see this, tell me why, I'm going to say, you're going to see this, we're going to watch it so you can see this, and then I'm going to ask you why. Okay? There are two places where that's going to happen. A couple billion years into the video, you're going to see things start to move a little bit more fluidly. And then about 600 million years, at 600 million years ago on this video, everything's going to start, wow. It's like watching someone dance. It's so fluid and just so dynamic, and everything is so specific and detailed, okay? So watch this, and let me know what you think. Okay, so right now it's pretty jerky. It's just kind of scattered around. And now you can see that we have more detailed movement. Still slow, not terribly dynamic, but better than before. Watch for when that first supercontinent forms. Atlantica, right there. Well, I mean, that wasn't the first one, but it's a big one. Okay, so things are starting to speed up a little. As time goes on, we can see more detail. Less of that rock has been destroyed through subduction or metamorphism. Okay, you're about to see the supercontinent Rodinia. This is the largest supercontinent that ever existed, as far as we can tell. Right about here. Oh, actually, we have a little more time. It's 1.1. They all separated and then come crashing back together. There we go. Right here, Rodinia. It's a lot of land all in one place. Notice all these colors, by the way. These colors correspond to the rock that now makes our current alignment of continents. Okay? So that green mass, that's North America. Pink, I believe, is Africa. There was a key at the beginning. Pink is Africa. Purple is Australia and Oceania. Yellow is South America. White is Antarctica. Okay, now we're coming up on that time at about 600 million years. You're going to notice things get really dynamic, really fluid. We're starting to see it, but it really takes off at about 600. Look at this. We can see so much more detail in the changing coastlines and the shapes of our continents, the creation of island chains, where before we couldn't really say much about that with any confidence. Look how dynamic and fluid this is. Dinosaurs are about to show up, by the way. Yeah, here's Pangea. Dinosaurs are here. Look, you can see the shapes of our continents already. Pangea starts to break apart. There goes North America. There goes Antarctica and Australia. There's Africa and South America have split apart from each other. And now, right, bam, dinosaurs extinct. And here we are. Wasn't that interesting? Okay. Now, at that about 2.3, 2.4 billion year mark, why do you think we were able to start putting more definition into how the continents moved and where they were at those times?
More data? Like,
More data from what?
From soil that we have.
from like the type of rocks and the movement?
We definitely have more data from the types of rocks. Less of it has been destroyed through tectonic processes, but there's also something else, a very important data point.
Fossils?
Fossils, bingo. The more fossils there were, the more data we had. At this point in time, there's pretty much just stromatolites, okay? Mats of algae. But where did that algae live? On the coasts of the continents. So where we find these collections of algae fossils, we can say with some confidence, that's where the coastline was at this time. And we can chart that through the fossil record, and that's where we can start adding more definition to a model like this. Now, what about at the 600 million year ago mark? Why do you suppose it was able to get so much more dynamic then?
Because living things started to show up.
Well, we already had living things, right? The stromatolites, but what changed?
They died.
No. What? Huh?
Dinosaurs?
Not dinosaurs yet, but new life showed up. Totally different life. About 600 million years ago, that's where we start seeing sponges and amoebas and all sorts of different other forms of life started showing up on the scene. Evolution really took off. Where stromatolites, this algae was the only living thing on the earth for billions of years, we think. All of a sudden, it started to change. And because there was so much more variety in the fossils, we were able to create a far more detailed picture of continental movements by determining where those fossils would occur. This is a desert species. Well, at that point, there wouldn't be a desert species. This is a shallow water. This is a deep water. This is a species that would prefer the beach. All of this data we can figure out because of the wide variety of fossils we start to see at about 600 million years ago. And it only got more and more specific and more detailed as time went on because evolution continued to make far more diversity in life. I'm hoping you're starting to see a theme here, which is the point of historical geology, to point out to you how the intersection of geology and biology is so important. Okay? How intertwined life and geological processes are to each other, right? Speaking of which, plate tectonics does something incredibly important because plate tectonics causes plates to run into each other, and one plate gets subducted under the other, and it gets pushed into the mantle, and it gets incorporated into the mantle, and then eventually that material makes its way back up to the surface through convection. It's recycling matter. Stuff that's been on the surface for who knows how long, hundreds of millions to billions of years, gets shoved down into the mantle and finally makes its way back up to the surface so many years later. What about carbon? Carbon often will get captured in the ocean and turned into calcium carbonate, right? And fall to the bottom of the ocean and turn into limestone. The limestone stays there until it gets subducted underground. That carbon is locked up in limestone. If there were no plate tectonics on our planet, we would have no more carbon in the atmosphere. Life couldn't exist without plate tectonics here because the carbon, instead of getting permanently locked up in rock, gets shoved down into the mantle and recycled back up to the surface. And that carbon can be released through volcanic eruptions and other processes. What about phosphorus? If you've taken any chemistry, I sincerely doubt any of you have taken organic chemistry. So here's a little tidbit that may be useful if you take that later. Every single one of your proteins that is used to create you, every cell, every genome you have requires phosphorus. Phosphorus is essential for life as we know it. Without a way to recycle phosphorus through the Earth's crust, eventually it all would end up either in rock or underground. It would get buried in things like sedimentary rock. And it would never come back to the surface, and that phosphorus can never be used to make new life. Life could have begun here on Earth and then simply died off because there wasn't enough phosphorus to keep it going, because it all got locked up. And instead, we have plate tectonics, and it recycles these essential elements back up to the surface over and over again. Intertwined, right? Life and geology. Okay. Convergent, divergent, transform boundaries. We all remember how that works. You got them run into each other. They split apart. They scrape past each other. Here's another close-up of convection cells and how that works. We can use current trajectories of plates as they're moving now to kind of try and estimate where they will end up in the future. This obviously is not including anything that may pop up between now and then, right? We have no idea if new convection cells will start, if old ones will stop, if they will change direction. We can't really predict that with our level of technology and understanding at the moment. But based on the current trajectories, in about 50 million years, we should have something like this. Australia has moved much further north. Africa has run into Eurasia. South America and North America are no longer connected through Central America. And then about 250 million years into the future or so, we should end up with something like that, where once again, we have a massive supercontinent. You remember when I talked about this last term? So anyone remember why Antarctica is still down here in both of these models?
No movement.
It's not moving right now, and it hasn't moved for a long time, about 55 million years or so. And so we really have no way of interpreting, or I guess I should say forecasting, where it could end up because we have no trajectory for it at the moment. So in every model, it stays down there. We already talked about all that. Okay. Some other evidence that our plates move. Hotspots. Hotspots like Hawaii are places where magma has essentially chewed its way up through the crust and has started spitting out on the surface, and it builds up volcanoes, and those volcanoes gain height. And if this happens in the ocean, eventually those volcanoes become islands. Like Hawaii. Hawaii is in the middle of the Pacific Plate. It's nowhere near a plate boundary. So why does it exist? Because there is a hotspot underneath the middle of the Pacific Plate, and that hotspot has pushed enough lava up to the surface that it made this chain of islands. Now, how does that help us to understand that the Pacific Plate moves? Well, look at the sequence of our islands here. They are in a chain. And the oldest islands are at the back of the chain. These ones back here, like Hawaii, 5.6 million years old. But the big island of Hawaii, Hilo, well, that's 1 million year old. Okay? 1 million, 5.6. Getting older the further back you go in the chain. What does that mean? The hotspot's not changing.
No, the plate's moving like that way away from the
Yeah, exactly. If I had a lighter and I held the lighter right here under this paper, so it burned up through the paper, and then I moved the paper on top of the lighter, but I kept the lighter still, I would have fire carve a line through that paper, right? The hotspot's not moving. The plate is. Evidence for the tectonic plate theory. Okay, plate tectonics. Also, there's the whole paleomagnetism thing. Okay, where I told you before that Earth's magnetic fields switch polarity every now and then. I'll come back to that in a moment if you don't remember that. But because when these magnetically sensitive minerals are formed, they are oriented towards magnetic north at the time they are formed. We can actually look at them and their orientation on the plates now. So if I'm looking at a plate, at a sample from the Pacific Plate, and it is oriented like this, that tells me at one point this plate must have been flipped over so that it could be pointing magnetic north if it's either up there or down there, right? So at some point, this plate has rotated such that these minerals are now pointing that direction. Same thing here, same thing there, same thing here and there and there and everywhere. Paleomagnetism as a way to determine what directions plates have changed as time goes on. Now we have the technology for GPS tracking as well. We can actually see the rate at which these plates move. About 5 centimeters a year, by the way. That's the same rate that your fingernails grow. Okay? Doesn't seem like a whole lot until we're talking about millions of years of movement. If you lived for 1 million years and you never clipped your fingernails would be about 5 million centimeters long. Right? That's how fast the plates are moving. Okay. Those magnetic field reversals that we see evidence of in the tectonic plate record, in the these I should say in the minerals that are made at divergent plate boundaries as a result of the convection cells moving these tectonic plates, right? They are recording the direction that magnetic north was at the moment they were made. And we can see where you'll have a strip of minerals that are pointing what is now magnetic north, and then there's some kind of switch, and the next strip of minerals is pointing magnetic south, and then north, and then south, and then north, and then south. In these sequences, these strips getting away, moving away from the divergent plate boundary. So our magnetic field switches polarities on occasion. Still trying to figure out exactly why that happens. But it happens, a major transition happens on average every 450,000 years. Seems to be the consensus. There are small ones in between that, but the major ones that last for a long time are typically around every 450,000 years or so. And as I mentioned in 1403, if you remember, we are in the middle of a transition right now, but we do not yet know if it will be a big one or a small one. Our magnetic north is about in the middle of Canada at the moment, and it's moving further and further every year. Picking up speed, actually. So we'll see what happens. All right, let's talk about faults for a little bit. A fault is caused when differential stress creates shear strain on rock. And it's just a simple way to explain this. I take a stick and I start to bend it. And because I'm bending it and adding that pressure, that stress to it, eventually it's going to snap. I overcome the material strength of that stick. I have added enough force that the energy built up in that material cannot withstand that energy anymore, or the material can't withstand the energy I've given it. Okay, sorry, I got a little tongue-tied there. Okay, and it snaps. Same thing is true for rocks. You build up enough strain, enough stress in a rock, and eventually it is going to crack. It's going to fracture and make a fault. Remember, a fault is simply a plane. It is not an object. It is not tangible. It's a line, right? It's where something was and no longer is. Okay, a fault is a crack. Then you have two fault planes on either, or you have one fault plane, but then you have the two sides of the fault, the hanging wall and the footwall, right? That's tangible. That's a substance. The fault itself is simply the crack. Okay. Faults represent areas where the stress builds up, and the stress is usually associated with tectonic activity of some kind. Okay. When the fault slips, you make that earthquake. Earthquake releases the energy that is built up along your fault plane, right? And then that energy starts picking up again. It starts over, and then starts over again, and then it starts over again. This is the nature of faults. Eventually, perhaps, depending on the way that the convection cells are going and the tectonic plates are moving, you may, things may change direction. Things may change such that you do no longer start to build that stress up, and so you have a fault that no longer experiences that buildup of stress. For the most part, though, faults generally, even if it's over long periods of time, still build that stress because they're there for a reason. They're there because the stress showed up at some point, cracking the rock to begin with. Okay. Mountains are formed as a result of different kinds of stress. You can have compressional stress, tensional stress, or shear stress, like what makes a fault. But regardless of the cause, when you do form a mountain, we call this orogenesis. Okay? Orogenesis, this word right here. Now, in my class, starting in Module 3, you're going to be learning about things called orogenies. And orogeny is a major mountain building sequence. Yes, associated with tectonics. Okay. I will only be telling you about the major orogenies that have to do with our own continent, North America. I could not possibly go over all of the orogenies that are relevant across geologic time with you, because I'd have to tell you about all of the ones that affected other continents as well. So we're just focusing on the ones that affected our own continent of North America. Okay. I'm going to let you know right now, it would be a very good idea, wink, wink, to keep careful note of the orogenies I tell you about and when they happen. Interpret that how you will. Okay, so we're going to talk about these specific orogenies, But real quick, let's go over how they happen, the different scenarios that they can occur in, okay? So you've got the convection, or excuse me, the subduction of one ocean plate under another, creating a chain of islands, a volcanic island arc on top of the overriding plate, right? Like Japan. Good example of this is Japan. Then you've got your Andean type, where you have the same process occurring, a dense ocean plate subducting underneath of a lighter, or I shouldn't say lighter, a less dense continental plate. Same process occurs, magma rises up to the surface, you get the same chain of volcanoes, but because this is happening under and in a continental plate, you're going to get felsic and intermediate material up here instead of mafic. And so you're going to build a very tall mountain range like the Andes, which is why we call this an Andean type range. Okay. Then we have accretionary belts. This is when those first two examples interact with each other. So a volcanic island arc gets shoved all the way across the plate and eventually runs into a subduction boundary between the ocean plate that it grew on top of and an overriding continental plate. And so your volcanic island arc gets scraped up onto the side of this continental plate. And that is called an accretionary belt. This is what California is. California is made out of dozens of islands that all got scraped up onto the side of North America as various other tectonic plates subducted underneath of North America. Right now, the Pacific plate and what's left of the Juan de Fuca plate are subducting under North America. Prior to that, there was another plate called the Farallon plate, and there have been presumably many others before that. Okay? But each one of them brought, I guess you could say, a party favor, right? They brought a gift. North America, thank you for hosting the subduction party. Here, have a volcanic island arc up on California, right? And then the last example, continent-to-continent collisions. So here we have our ocean plate subducting under the continental plate. Okay, all well and good. Oh, but wait, there's another continent on this side of the oceanic plate. Crash into each other, right? And you get your Himalayas. Yes?
So the water that's into the two plates, it just gets evaporated?
The water that goes down under the plates?
Well, like, because there's an ocean in between the two continents, right?
Yes.
So, and if the oceanic plate goes under, right, does the water follow with?
Some water that is in the rock of the ocean plate definitely goes under. And it's that water that mixes down here with the mantle rock and lowers the melting point and allows magma to come up to the surface. But most of this ocean water does not go under. No. It's going to get kind of, this area is going to get narrower and narrower and narrower, and there's going to be less and less space for the ocean. And so it's going to kind of make its way out to wherever the rest of the ocean is, right? And so finally, the two continental plates collide like that. Yep. And then we've got isostatic adjustment, which is when, remember my example of the memory foam pillow that I gave? If you put a bowling ball on memory foam pillow and then take the bowling ball off, the memory foam slowly rebounds back upward. The same thing is true of crust. So if you have an extraordinarily large weight on your crust, like say a mountain range, it's going to shove its way down into the mantle somewhat. But then as that mountain range starts to weather and erode, mass is removed from the top of your mountain range. Isostatic adjustment is going to cause the bottom of your mountain range to rebound upwards, which is why we still have some very ancient mountain ranges on Earth today, like the Appalachian Mountain Range is very, very old. But if you ever go to the Appalachian Mountains, what you'll find is it's made out of deep crystalline rock, metamorphic rock from inside of an ancient mountain range. That's what's left because isostatic adjustment basically pushed the roots of those mountains up to the surface to where they are now. Rift basins, something that I mentioned already earlier today. When you get new convection cells underneath a continent, and these convection cells are moving opposite directions, it's going to cause your continental plate to stretch, and it's going to get thinner, and it's going to get faulted right here where it is stretching. And the mantle underneath of that stretched, thinned crust is going to melt because it's under lower pressure at this thinner zone. And that magma is going to come up, and that magma is going to be mostly mafic, because it doesn't have a great big thick continental plate to go through now, right? And so this mafic material is going to get deposited there in that valley. And as it continues to widen out and the valley gets bigger and more mafic material is piled up there, water is going to congregate there. You're going to get great big lakes like what we see out in the East African Rift Valley right now, right? You're going to get oceans start to flood in here eventually. And this is now the birth of a brand new ocean plate. And these two get shoved further and further apart. This is what happened to push Africa and South America apart from each other. This is what's happening in East Africa. This is presumably what will happen along the Rio Grande, okay, where that Rift Valley is forming. And then you end up with an ocean. This is the Atlantic Ocean, essentially, okay? As you, or I should say, as tectonic forces continue to build and mold and manipulate and stress, you're going to get some folding, you're going to get some faulting, you're going to get all of these different changes occur within your layers of rock, okay? We already talked about the folding, or the faulting. Remember that folding is what happens when you exert stress, usually compressional stress, on a linear feature, like a layer of rock. You put stress on it, it's going to bend up or down. It's called a fold, right? Whenever that sort of stress happens not in a regional area, so if this area represents a continent and there's tectonic stress on it causing some compressional stress from the sides, yeah, your layers of rock are going to fold up and down, right? But what if instead of being a widespread area like this, I have something poking up through part of this plate, like a magma chamber making its way to the surface, okay? That'll make a dome, a local area of deformation instead of a widespread area, okay? So you get domes and you get basins. These are different features we can see on tectonic plates. A basin is what forms, it's kind of the opposite of a dome, where a dome is when something gets pushed up and makes a kind of an arch shape, like it's a dome. Like if you turn a bowl upside down, right? Local uplift area that has arched and folded the layers of rock, okay? A basin is the opposite. You start with a low point, like maybe a lake or a sea, okay? And that lake or sea fills up with sediment, or a valley, okay? It fills up with sediment. Sediment gets deposited layer upon layer upon layer upon layer upon layer upon layer. And then eventually at some point, you're going to end up with what was once a low point is now pretty well filled up with sediment. No longer a low point. That sediment turns into rock, and we can see that in the fossil record. It's kind of this bullseye shape, okay, where you have your youngest rock in the middle and your oldest rock on the outside. That basin would not have formed without tectonic processes. So whenever we find these basins, it's very useful because we can use the information contained within that basin to figure out what formed it in the first place. Any questions about that? Yeah.
So Permian Basin, right?
Permian Basin.
What's like the oldest sediment found here?
If you go deep enough, there's still some pretty old sediment here. It's called the Permian Basin because it was filling up with sediment during a time period called the Permian, okay, which was the time period just right before when dinosaurs showed up, okay? So during the Permian, as you will learn about in coming modules, there were reptile-like animals, we call them, things like archosaurs, pelycosaurs, that had characteristics similar to modern day reptiles and characteristics like dinosaurs. And dinosaurs and modern day reptiles split off from this same common ancestor that these ancestors that lived during the Permian. But in the ocean that existed here during that time, there were many massive coral reef communities, right? Like the Guadalupe mountain range. That's one massive coral reef community that lived during the time when all of this was covered in water. And then shortly thereafter, this place got really well filled in with sediment, and it's been largely landlocked for a long time since then. Yep. Good question. Anything else? No? All right. Well, then I'm going to end lecture here, and we can use the remaining time for lab. You don't get lab 2 until next week, so we're still just working on lab 1.